Hey guys, Chili here. Welcome back to the second installment of Red Pill. If you don't know what the fuck that means, that's basically what I call my my low-level, detailed background videos. They generally deal with, like how the compiler organizes variables in memory, how the CPU accesses memory, the actual machine instructions, all that bullshit. It's not at all is it necessary for you to understand this stuff to follow along with my main series or to learn C++. But for those of you who are interested, I give these little talks every now and then because, I am also interested in this bullshit, and it helps to a certain degree to understand what's going on. Again, not compulsory in the least, but it doesn't hurt either. Just know that if this stuff is going over your head and you're like, fuck, I have no idea, just forget about it. It's not important. Move on with the normal videos. So, the first Red Pill video that I did was after I introduced you guys to variables and how they are sort of actually laid out in memory, the different data types, their sizes, binary, all that bullshit. I did a Red Pill video on that, showing the actual details. And now I'm going to do a Red Pill video. This one is basically a companion video to the pointer tutorial. That's intermediate tutorial 2. So I've written a whole bunch of code here. It's mostly to do with pointers. Hopefully you should understand what all these operations are doing already. It's kind of a prerequisite to watching this video. You should understand how pointers work in the first place. Now I'm going to give you a little bit more. We're going to peek behind the curtains and see what's actually going on here. So we'll put this in debug. We'll start her up. And so now let's look at the disassembly. This is where we're going to be spending most of our time here. So what's going on? Well, we got a whole bunch of local variables. So the first thing we do is we create a local variable n. We store a big old 69 in there. That's 45 hexadecimal. So you can see here this EBP minus C. This corresponds to the variable n on the stack. So we initialize n. Now we are going to initialize our pointer pn to point to variable n on the stack. So the first thing we do is there's a function here called load effective address. Not a function, it's an instruction. And what this does is, well, let's take a look at the move instruction. This is for accessing memory, for loading and for storing. So when we want to move, let's say, an immediate value, like 45, into a space in memory, we don't just have to give it an address. We can give it a calculation that it makes in the move instruction. So in move here, we tell it, put 45 hex into EBP minus 0C, and it will perform that calculation for us. Now, what load effective address does is it says, okay, I want you to use the calculation, the address calculation circuitry to calculate this address, but then I don't want you to do a memory access. Just take the calculated address and jam it in the place where I tell you. So it's like a move instruction, except skip the move part, just calculate the address and then put that somewhere. So we're calculating the address of EBP minus 0C and putting that in EAX. And if we step over here, so here is the address of our actual n variable on the stack. This is its actual address. And so we calculate the address, put in EAX, and then we store EAX into EBP minus 18, which is, I'm assuming, that is where PN lives. So we store the value into the pointer variable in memory, and there you go. Now, to actually use that pointer, what we're going to do is, again, we're going to load the pointer from its variable on the stack into a register, into EAX, which was useless because it was already in there from before, but again, we're in debug, we're not doing any optimizations, really. So we load the pointer, and then what are we doing here? Then we're going to load what is at the memory address pointed to by the pointer. So here we're loading from memory pointed to by EAX, which is going to load the value of n into ECX. Then we're going to add some number, right? Because that's what we wanted to do, right? It's pn plus and equals this number here, whatever this evaluates to, 15F hexadecimal. So we perform the operation of adding, and now we got to store it back. So again, there's no optimization. So the compiler again loads the pointer. This time it loads it into EDX for whatever reason. And then it stores the result of the calculation, ECX, into the memory location pointed to at by the pointer value that we just loaded. And there you go. Changes to 420. Beautiful. Now, one more thing I want to show you is the difference between a reference versus a pointer. So here I'm creating a reference RN, initializing it to N. Again, we load effective address EAX EBP minus 0C. Exactly the same as initializing a pointer, and then we store that into some place in memory, exactly the same as initializing a pointer. So you can see here, in this case, the compiler is implementing the reference exactly like it's a pointer. It's just a pointer under the hood, only it's got more limitations, it's safer, it's sexier, but it's still a pointer. Now I want to let you know, this is not always the case. The compiler is free to implement references in a number of different ways. As usual, the C++ standard is pretty vague and open when it comes to how references are actually implemented. So it doesn't always have to be implemented as a pointer, but usually it's going to be a pointer. And yeah, it just looks the same as the implementation here, is the same operations as you do on a pointer. So if I do this kind of plus and equals operation, again, load the pointer value, load do the indirection, load the value it's actually pointing to, do the operation, which turns out to be a subtraction operation here, because I guess when you evaluate this out, it's adding a negative number. So the compiler turned that into a subtraction, and then store the result back into, you know, the thing pointed to at by the reference. So again, I just did this to show you guys that references basically the same as pointers, they're just safer and they're sexier. Pointer arithmetic, so let's increment pn, we load its value, we add 4, because why do you think we add 4? It's because it's a pointer to integer, right? So we're moving one integer over, that means incrementing means adding 4 to its value. And then once we do that, we store it back into memory, where the pointer variable is stored. And if we wanted to add 5, again, that is just load, add some value, which is 5 times 4 is 20, 20 in hexadecimal is 14, and then store that back. No difference. This pointer arithmetic bullshit, you're just adding to the, basically to the integer address of the pointer. Array indexing. Well, let's first of all, we're going to initialize an array, so it's going to move all of the values into the array locations on the stack. And then what are we doing here? So we're going to make a pointer point to the beginning of the array. So we load the effective address of the beginning of the array, which is EBP minus 48, right? Minus 48, that's the start of the array. And then we store that. And we're going to do the same for a different part of the array. So what are we doing here? This is indexing 4 into the array and then loading that address into PA2. So we move 4 into EAX, that's the index. We shift left by 2, and that multiplies by 4. Binary shift left multiplies by powers of 2. Shift left by 1 multiplies by 2. By 2 multiplies by 4. By 3 multiplies by 8, etc. So this is performing the index calculation. And then here we're going to load effective address by going EBP minus 48, so that'll give us the start of the array, plus the index into the array, which we calculated here. And then once we have that effective address, we're going to store that into PA2, which is again EBP minus 60 hexadecimal, I guess. Then when we access using PA2, is the same story. Load the pointer and then use the pointer to store into memory. The pointer value, the address. Load the address from the pointer, use that address to store into memory. So let's step over this stuff, make sure it works. Yeah, you get your shit. You can see all the shit happening in here. It's all good. You can trust Chili. Chili ain't gonna lie to you. Yeah, that's loading that. There you go. You can see the memory address changing in here. Use that to access some memory. And PA2, if we look into the, where's the array? ARR, there it is. You can see it has been changed to 69. The 0, 1, 2, 3, element 4. Change 69 just like you would expect. And again here, if we want to, we're going to index off of pointer PA1. So how does that work? Well, first off, we're going to calculate the index again. Load 4, multiply by 4. Then we are going to load the pointer into ECX, pointer value. And now it's just ECX plus EAX, right? It's just because the pointer points directly to the start of the array, you don't have to calculate, you know, EBP minus 48. It's just ECX and then plus the calculated index. And we load some value to there. 420 in hexadecimal is this, in case you really need to know that information. There you go. And that has changed it to 420. What's next? Okay, so pointer distance. How does this work? Well, it's just subtracting two pointers. So you move the value of one pointer into a register. Then you subtract the value of another pointer from that. And then you are going to shift right by 2, and shifting right is a fast way of dividing. So doing this pointer distance is basically subtract 2 pointers, then divide by 4, because if you don't divide, you're going to get the distance in bytes, but you want the distance in elements, in this case ints, or PA, these pointers point to ints, right? So you want to divide by 4 to get the distance in ints, and it does that by shifting. So even the even debug mode does a little bit of optimization. It doesn't use the division instruction. It would use the division instruction if it weren't a nice power of 2, but since it's a power of 2, it can use shifting. And then, you know, it moves the result onto the stack corresponding to dist. Great. Let's move on. All right, pointers to pointers. Again, there's no difference here targeting a pointer to a pointer. You still load the address of the thing you want to target, load effective address, and then you store that into the place on the stack corresponding to the pointer variable. No difference there. And yeah, see, we're doing it now with a pointer to pointer to pointer. Again, no difference. This is just a negative number, but for some reason it has detected it as a positive number, and so it looks stupid. But it's actually just subtracting some value. So now what am I doing here? Now I am retargeting PN from the pointer to pointer to pointer. So I'm dereferencing it twice, which indirection gives me the pointer. And then I'm going to set that equal to ARR plus 6, which should make it point to this element here, the last element of the array. So what we do is we load effective address of, what is this now? This is going to be, I don't even know what this is. No, I see. EBP minus 30 is the last element of the array. So what it's doing is it's doing a little bit of an optimization here. Where are we? Here it is. It's doing a little bit of an optimization in that it doesn't have to calculate. Well, it knows where ARR is on the stack. It's just EBP minus 30. So this is loading ARR into EAX, I guess. Not an optimization. Never mind. Chili's brain is broken a little bit. But we're loading, yeah, the last element of the array. Yeah, it is an optimization, right? Because this is pointing to the beginning of the array. So it's basically going, you know, what is it? EBP minus 48. And then it's adding 6 integers worth of bytes to that and arriving at EBP minus 30 directly, and it's loading that effective address into EAX. And then, what is this? This has got to be PPP, right? So now it's loading the address stored in PPP into here, right? Yes. And so it's got to dereference that twice. So now it looks at that address and stores that value into here. So this is the address of PP, right? And then we go in direction from PP. This is the address now of P. So now we have the address of P, which is what we want, PN, right? So now we store this value here, this calculated address, into P, because EDX is right now pointing to P. All right, so there you go. We did it. We solved the mystery. Now, if we want to, that was double indirection. If we want to do triple indirection, what we've got to do is we've got to load the address stored in PPP, and that is the address of PP. So then we load the address stored in PP, and that will be the address of P. Then we load the address of P, the address stored in P, and that will give us the address of the original target, which was the last element in the array. And then we can use that pointer to store our value. So you can see here, the more indirection you have, the more of these loads it has to do. We call this pointer following, where it's got to find out where this pointer is pointing to, load that address, then use that address to find out where that's pointing to, load it, and you keep following until you reach the end target. And then you can actually do your memory store. All right, now let's take a look at, this is the code that we were just looking at. Let's take a look at the stuff that we're going to look at next, which is we're going to create an array of objects of class bullshit, and then we're going to call the function func, passing it the address of one of those objects in the array. So the func class, it's just got a few simple members here. They're all public access. A couple of ints and a car array. It's got a function here, wow, we will look at that in a second. So we got this class, just got a few data members in it, and we got this function func that is going to set some of those data members. One of them, so it's going to set it using, what am I thinking here? Compile time indexes here, indices, and a compile time value. And here it is going to set using runtime indices and a runtime value. And so we'll see the differences between that, if there be any. Oh shit, I forgot one thing in here. Now I'll show it to you at the end. Anyways, so let's go back to, I guess let's step over this stuff. We've already done it. It all works as usual, as you would expect. Now let's take a look at this disassembly here. So go to disassembly. And so what we're going to be doing here, initialization of the members of this array. So it just gets straight to the business, which is it moves 20 into EAX. I believe this is going to be perhaps the size of, yeah, this will probably be the size of a single object of type bullshit. So it's going to be, it turned out to be exactly 32 bytes maybe. And then what we're doing is we're shifting left by 1, which again multiplies by 2. So that gives us the index. So here it's calculating the index. Here it's loading the effective address by adding the index to the start of the array, which is this plus this. Again, it's misdetected it as a positive number when it should have really been a negative number. But here we're pushing ECX onto the stack. So we're pushing the address onto the stack, calling the function, and here it cleans up the stack afterwards. So let's step into this function call, shall we? Step in, and again you get this weird sort of jump table bullshit. I don't really know why. I'm sure there's good reason for it. And now we're in the function. So again, the preamble, you know, you preserve the base pointer, you set up the new base pointer, and you reserve a bunch of space onto the stack by subtracting stack pointer. And you preserve some other registers. And here is some other bullshit that is mostly just for, that gets set by default when you're in debug configuration. You can disable this. I should have disabled it probably, but it doesn't matter really. We can work around it. So, first things first here, it's going to calculate some indexing. So this is more complicated because you got to index into an array, you got to index off of a pointer, then you've got to access member, then you got to index off of that member. So it moves 20 into EAX. That's the size of an element. Then it's going to multiply that by 3 because the index is 3. And then it's going to add, what is it adding here? Add to ECX dword pointer EBP plus 8. Don't really understand why it's, I don't understand. This is the pointer that we passed in. So this is the pointer to an object, right? To a bullshit object. So this is the pointer we pass in. We can tell because it's EBP plus something, and that usually indicates that we're accessing a parameter that was passed in on the stack. So here we're adding the pointer to the indexing offset, basically. And then we're going to move the value of 1 into EDX. 1 is the size of a byte. We're going to multiply that by 7. That gives us the second index. And then we are going to move the value, I guess this is 6699. No, that's not 6699. That's not that thing, is it? I don't think it is. Multiply EAX, ECX. Yeah, so ECX is the start of the array, right? Yes, that's going to be the start of this array, ECX. And then we add EAX, which is the offset into the array that was calculated here. And we add 4 because, of course, in this calculation here, we hadn't yet considered that this is actually the second element of the object. So it's got to offset by an additional 4 because we're going 4 into the object. That's where the array starts at, and that hasn't been factored in yet. I don't understand why this is 2b, though. 2b is not 6699. That is... Oh, wait. Okay, I understand now. I'm an idiot. I'm a fucking retard. I'm trying to put 6699 into a car. Cars only store up to, you know, positive 127 down to negative 128. So, yeah, I'm an idiot. And this is what you get when you try to put this number into a box that don't fit big numbers. You get this. You get this thing here. So, there you go. And now, with this thing here, what we're doing is we're going to be calling the insertion operator on cin. So we're going to be loading stuff from the console. So what we're going to be doing here is load effective address EBP. So we're pushing onto the stack. I don't understand why it's moving the stack pointer into SI every goddamn time. But I do understand this. This is loading the address of these, where are they? Val, I, and J. It's putting those addresses onto the stack. Why is it putting them on the stack? Well, because it's going to be calling the function that will do the insertion operator, that will read input from the console and convert it into integer values and store it. So it's putting the destinations onto the stack. I believe the insertion operator is, it takes a reference, right? Reference to the right-hand side. That's what we're doing. We're pushing those pointers onto the stack. So we'd set that shit up, and then we're going to call. And when we call the function, now our window comes up, and it says, give me some numbers, bitch. So let's give it some numbers, 420, and we'll just put some simple indexes in here. Let's say 3 and 7. Again, press enter. We will be back into the debugger. And now subsequent calls will not block because they will already have information in the buffer. But it's not important. What is important is that what happens after this, which is all the indexing bullshit. So we're gonna load the address of EBP. What is pointed to in here? What is this? This has got to be one of those. Yeah, so I don't know which one is which, but it's going to be one of probably I and J. So this is probably maybe I, and then we shift left 5 times, which is a big multiplication. Probably multiplying by maybe 32, I would guess, which is the size of one of those objects. So we multiply that, and then we add to that the pointer to the original pointer that was passed in. And then what do we do here? We're loading, moving, so this is J, probably. J, and then for our good old friend J, we're gonna move. Here we're loading the value that was input, I believe. Where is it? Yeah, maybe this is the value then. This is the value that was put in. And these two are I and J. I don't know. I don't know which is which, but here we're doing move byte. Yeah, so here's where it's actually being stored. EAX, ECX plus 4, which is the same as we had before up there. So yeah, we're loading that into EAX. We're loading J. Right. So it's actually done a little bit of an optimization here because it's realized for some reason that it doesn't have to multiply by 1. Remember up here, it was loading 7, multiplying 7 by 1, which is just going to be 7. So for some reason here, it has optimized it slightly, and it's skipped the multiplication because it knows that it doesn't have to multiply by 1. Anything multiplied by 1 is just that thing. So, yep. So that means that ECX that's got to be J, right? And EAX is going to be the I after it's been calculated. Then it's just the pointer that was passed in is ECX. I'm all mixed up now. EAX, wait a minute. Oh yeah, EX is the calculated I indexing plus the pointer that was passed in. And then this is the indexing into the array. And then so here we have the address plus the indexing into the array plus 4 because we have an integer before we start with our array. And this DL contains the value, and we just put that in there. It's all good. It's all good. All right, that was really complicated, but that's the way the cookie crumbles when you're looking at assembly code. Now, one thing I wanted to point out here is that if you remember when I explained the simple version of all this pointer bullshit, I told you that when it calculates an array like this, an indexing, an address, when it calculates an address, if it knows all these values at compile time, it's not going to, perform a lot of calculation. It's just going to store the value directly. But here we see that even with compile time stuff, it's still doing all the calculations. And the reason for that is because we're in debug. Now, we can switch it into release, but it's not going to be nice because when you put in release, it's going to take all the code from this shit and it's going to jam it directly into here. And then it's going to go through all this bullshit, because when we build and release, it's going to take all this code in here and it is going to jam it directly into here. That's called inlining. And then it's going to look at all the emitted machine instructions and try to simplify them and optimize them. And it's going to jumble all your shit up, and you're not going to be able to follow along very easily. All your shit's going to get mixed up together. Like, let me show you here. If I step into this, it's got to build a little bit. And if I go into disassembly, first of all, you're going to see here, you don't get any function calls that call our good old friend, where was it? There's no function calls that call func in here. You can see here function calls. These are calling the insertion operator for cin, but it's not calling our function. Let me prove it to you. Let me put a breakpoint in here. Run that. Nothing. Let's put some numbers in here. Let's put a 2 and a 3 and a 3. And program exited. It never stopped inside the function in here, because this function no longer really exists. It's been inlined into this function, into the main function. So, and that's not all. Like, I mean, when you put it into release, it is going to detect that we calculate a whole bunch of shit for n, but we never use n anyways. So what it does is it basically just removes all those instructions. There are no longer any, there's no longer any code in here that corresponds to these calculations that we're doing on n. Where is it? I can't even tell where the start of the function is anymore. But yeah, I see all this stuff here. Well, not all this stuff. Main. Yeah, see, it starts main and then it goes here. It skipped all that stuff with n. All this pp stuff, that's all gone. This is for calling func. And that's all that matters here. So it's hard to figure out what's going on when you're getting your shit inlined and the compiler is just removing whole parts of your code because it realizes that it's not doing bullshit. It's not doing jack or shit. So what you can do to prevent the compiler from inlining your bullshit is you can go _. This is decal spec, no inline. This is specific to Microsoft Visual Studio. There's going to be for GCC and for other compilers, it's going to be different. But did decal spec? No. Decal spec, no inline. And when this tells the compiler you're not allowed to inline this fucker. So you're going to have to make a function and call the function. And when we do that, now we should have a function and we should be able to break at our function. And we can go to disassembly. All right, it seems here is the instruction that corresponds to this movement here. But what I want to know is what ESI, where does that get? That gets set here. So ECX must be the pointer, the pointer that we pass in. But where is ECX set? Because I don't see it set anywhere up here. So that means that this function might not be passing in the pointer, and when we go into release mode, it might not be passing it in by the stack. It might be passing it in directly in ECX. So what we can do is we can go and look at where this function is called. D81002. So we go into main and we look at the call D81000. Nah, this is probably the one, right? So ECX, so it's loading EBP plus whatever into ECX. Now what I don't understand is what is all this other bullshit in here? This is other stuff from, like we were loading a 69 in here somewhere. This is from somewhere else. This is just other bullshit. Move. But here we can see that it is actually passing in that pointer by register. And here we can see that all this indexing here, this 3 and 7 indexing, that's all just pre-calculated by the compiler at compile time and just all calculated out into a single plus 6b. But you can see here that the runtime calculations, they couldn't be optimized out because the compiler doesn't know what number the user is going to input. So it has to do the multiplication by 32 and the addition and all that other shit. Well, that's the multiplication by 32. There's some addition here, some more addition here. It's all good. It's all good shit. All right, let's get out of release mode because that's hurting my brain now. And we're just going to go back into good old debug. And we're going to look at the last thing, or the second last thing on my list of shit to show you. And that is what happens when you call a member function on an object. Because the idea, well, this member function here, wowie, what this is going to do is it's just going to set z equal to some value in the object. Now, the thing I want you to think about is, so member functions are basically the same as any other function. It's just instructions in memory. You call them, the CPU will jump to that point, execute the instructions. So how does it work? How does it know which object's z to change? It's going to set z equal to this one, but how does it know which one? There is no parameter here. There's no pointer to the object. And the answer to that question is there is a pointer, but you can't see it. So when you call a member function on an object, there is a secret parameter that is passed in, and that parameter is generally passed in register CX. So ECX if you're in 32-bit mode. And let's see how that works. So first I gotta do the input bullshits. So I don't know. 2, 2, and 2. It's fine. It's fine. Now let's look at the disassembly. So here we're going to move 32 into EAX, and we're going to multiply that by B, which is 11. Hexadecimal B is just 11 in decimal. So here we're doing calculating the index offset in bytes from the beginning of the array. Then we're going to load the effective address of the beginning of the array, which is EBP plus this bullshit. We're going to add the offset, and we're going to load that into ECX. So ECX now contains the address of the object on which we're calling the function. Then we call the actual function. And step over that, step into, step over. And again, we do your preamble bullshit, all your dumb shits. And then it pops ECX. That's interesting. Did it push ECX before? Yeah, it pushed ECX. It did some weird bullshit. Then it popped it. So it just preserved it to do some bullshit here. Whatever. So ECX contains the pointer to the object. And then it just says, okay, well, move ECX into EBP minus 8. That is like a local variable. Why is it moving it into a local variable? Moves ECX into local variable, moves local variable into register, then it moves this value into place pointed to at by the register plus the index into the object, right? Because I guess Z is going to be 1C bytes into the object. I don't know why it does all this hanky-panky in here, but you know, debug mode has its quirks as well. But anyways, that's the general thing that I wanted to get across, is that is how member function calls differ from standard function calls. They have a secret parameter that is passed in, and that's the pointer of the object, pointer to the object on which you called the function. So the left-hand side pointer to that object is passed in to the function as a secret parameter. Now the last thing that I wanted to show you is what happens when you make a pointer point to a global variable. And that works, let's just do quickly. Pn is equal to address of global. And if we do this and we look at the disassembly, fuck, I gotta put the numbers in now. Yeah, that's the wrong key, isn't it? 2, 2, there we go. Fair enough. So let's go to disassembly. And what this is going to do is it doesn't do the hanky-panky of load effective address and then store. It can just store the address of the global directly into the pointer on the stack. And the reason why is because if you're using local variables, they're all defined relative to the base pointer. So the first thing you have to do is you have to do a, where's one of the simple ones here? Can't find my shit in memory anymore. Where is a simple one? Please. Yeah, maybe like this. Yeah, load effective address EBP minus 18. So here it's got to calculate the address of the variable relative to EBP. So it has to do a load effective address, but with a global variable, the address is just fixed. It's static. And so it can load that value directly into memory, do it in one operation, much like I showed you in the original, the pointer video, the mainline pointer video, where I wasn't talking about, you know, base pointers and all that bullshit. So that is actually the case when you're working with global variables or static member variables, anything that goes into the static storage. And that's it for today, I guess. Just generally a look at a bunch of different bullshit on the stack and in memory with pointers and addresses and all that dumb bullshit. It was a little hairier than I wanted it to be. Some things didn't quite line up smoothly, but you get the general idea. I hope. And again, if you got any questions, you can always ask me on the Discord, on the forum, and I'll give you answers to all your questions about all this dumb, low-level bullshit. Anyways, hope you liked the video, and I will see you soon with some more C++.